All right, let us begin. Welcome everyone to the Integrable Systems Seminar here at BIMSA, and it is our great pleasure to have Frank Nijhoff from the University of Leeds and Shanghai University, who will tell us about the elliptic lattice KdV equation.
Okay, well, thank you, Anton, for the kind invitation to give a talk here in BIMSA. Kind of a place I've heard a lot about, but it's the first time I've visited. And I was kind of suggested, I think, to talk about this elliptic lattice KdV system, which we had a recent paper with Da-jun, Zhang, and Cheng. And microphone. Oh, is it not working? It is working, I think. I'll try and talk into the microphone. And this is part of a program on, long-standing program on studying partial difference equations on the lattice, so equations in multiple directions on a space-time lattice. And there are a number of what we call elliptic integrable systems where the system itself is given in terms of an elliptic curve that is separate from the issue of whether there are elliptic solutions to the equations involved, because many integrable equations, they have elliptic solutions, like KdV, for instance, but these are equations which themselves are defined through an elliptic curve. And this is in part an old result. So this is about this system over here, which looks like a very complicated system. And I have to explain a little bit the notation. So this involves three dependent variables, three fields, U, W, and S. And my notation always for lattice equations is like this, that I use tilde and hats to indicate shifts in the independent variables on the lattice, so in the direction n and direction m, and here we have a combined shift. And so this system is actually on a quad lattice, so it involves 4-point around elementary quad, but in three different components. And P and Q, they are important as well. They are the lattice parameters, so they are parameters that are associated with the directions in the lattice, so with the grid width. So P is associated with N and Q is associated with M. That is important to remember. And this system is rather complicated and daunting looking. So it involves 5 equations. Actually, this one should also be shifted in the horizontal and vertical directions, these last two. And these last 2 equations, they are on the links of the lattice, and then we have 3 equations which are on the quad, so it involves 4 points along a quad. And the outstanding feature here is that there is an elliptic curve here, which is given by this function r of x. And this is maybe doesn't look immediately like an elliptic curve that you may be familiar with. This is a rather strange way to parameterize what's actually a Weierstrass elliptic curve. So I'll give the parameterization later. But in this form, the Weierstrass curve appears actually in several integrable systems contexts, in particular also in the work by Data Jimbo Miwa of the early 1980s on Landau-Lifshitz. And what I want to point out here is that so G and E are related to the moduli of the elliptic curve. In fact, E is a branch point, and G is the product of the differences of 2 branch points. So if G goes to 0, then the curve degenerates. And in that case, actually, we see that the first equation, this term here, will decouple from the rest of it, and we are only left with an equation in terms of little u. And that is a well-known equation in the well-known ABS list of quadrilateral lattice equations. So actually, it is the very first equation in that list. So this is the list of classification that was studied by Adler, Bobenko, and Souris in around 2003. they came up with a list of quad equations, scalar quad equations, which have an integrability aspect that I will mention later. And this equation in that list is denoted by H1, and it is the simplest of all the equations, but it already appeared much earlier in the work, for instance, of Wahlquist and Easterbrook as the permittibility conditions of the Backlund transforms for the KdV equations. So this actually is what you could consider to be a discrete potential KdV equation, so without this S term. But when you switch on the modulus, then this gets coupled with the S, and then there's a whole raft of other equations that come into play. So then the question may come up, why would you consider such a system that is so complicated, and why venture into this direction? Well, of course, the age-old math imperative, if you can generalize, you must generalize. And in fact, it gives an indication that maybe this potential KdV or this quad lattice equation is just a top of an iceberg, below which under the water you have a huge other iceberg which you can hit, and which pulls into questions all kinds of results that we know about the quad lattice equations. So the quad lattice equations, scalar ones, were pretty well studied. There are lots of things known about them, but not so much about this extension to higher components, and that comes along with the elliptic curve. So there's another equation, a well-known equation that has an elliptic curve in it, which is in the ABS list, namely the top equation, which is Q4. And if I have time, I'll come back to that and explain how that relates or not relates to this system. So the kind of question that I want to answer is things like, why is it integrable? And it is integrable in the sense of multidimensional consistency. That is the property that when you extend the lattice from a two-dimensional lattice to a multidimensional lattice with more lattice directions, and you impose the same equation, only changing the parameters associated with the directions, but you copy all the equations, and then there's a consistency check that holds, and that is a very special consistency check, and that is a sense of in which these equations are integrable. So that is what we call MDC, multidimensional consistency, and it's a very strong property which limits the number of equations very strongly to the integrable cases. But apart from that, there are also other integrable aspects that are well known, like Lux pairs. And for instance, also the existence of multi-soliton solutions. So then the question is, why is this at all interesting to look at such a complicated system? Well, as I said already, a number of features it pertains, but actually compared to the well-known quad lattice equations, there are a number of aspects that no longer hold for this system, and that puts into question what are general aspects of integrability that play a role in this in general quad lattice equations, or lattice equations of a more general type of higher rank. So what I mean is that you have an equation on a two-dimensional lattice with parameters. These are these parameters P and Q. And now you add other directions, but you associate with each direction of its own parameters, say P, Q, and R, for instance. And then you have a kind of consistency around the cube. So you impose the equations on faces on the cube. And then there is a consistency check, because you have various different ways of computing. It interturns, yeah, on all, well, you can, then it extends to the whole lattice, yes, indeed, yeah. Yeah, so there are a number of things that I will point out that works for this scalar class of equations, but no longer works for this elliptic extension. And so there are all kinds of new phenomena that appears actually in this elliptic KdV. And then a question would be, to which I don't have an answer yet, is it related in any sense to these Q4 equations, of which we also know very little at the moment. So if I have time, I can point out what we do know about this Q4 equation and then make a kind of comparison. Okay, so let me first come back to to the system. Again, I had it written down, but it's behind the screen. So it contains these 5 equations, but actually these are 2 double equations because they live on the links. And then we have these 3 quad equations which couple S, W, and U. But there is also redundancy in the system. So I will later show that you actually can bring the system down to a 2-component system at the expense of making it of higher degree. And then specifically these equations that live on the link and that involve the curve, they are important when you do reductions to periodic solutions. Okay, so what other systems are related? Well, if you look at continuum limits, there are various ways of doing continuum limits, so shrinking the lattice in one particular direction. And there is a technique that we call the skew continuum limit that produces this differential difference equation. So this is discrete in still one direction, so that's indicated by the tilde shift. The under tilde here means the opposite shift so the shift in the backward direction. But then there is a continuous variable that has appeared, which is visible here in the S dot, which is a derivative with respect to that continuous variable. So this comes out as a continuum limit from the system, but it is not only a continuum limit, it is also compatible to the original lattice equation. And this is like a Toda type system. So it is associated actually with Volterra type equations, but move to the elliptic case. And if you take a full continuum limit, then you can arrive at these systems. Here it is already written in terms of a 2-component system, where this capital U is this combination U minus W over S. And in all these formulas, this R is this rational function that appears. Now, one shouldn't worry too much about zero denominators here, because the zero denominators mainly appear by the attempt to write the equations in a kind of elegant way, but they can be multiplied out in cases that S is 0. Okay, so that is one type of associated semi-discrete equations, but you have also another kind of semi-discrete equations, which you can call an elliptic dressing chain, and which looks like this. So this comes from what we call a straight continuum limit, and then it has a slightly different aspect to it. But when we take G equal to 0, so when we remove the elliptic curve, then we get this equation only in terms of U, and that is the traditional dressing chain, or associated with the Backlund transform of the KdV system, the original KdV system. But you can use this system of equations as a way to compute, or you can consider this as a Backlund transform, namely the transformation from U to U tilde can be considered as a Backlund transform on a solution U. And to see how you can apply that is by taking a very simple seed solution, which contains U0, S0, and W equal to 1. Then the system breaks down for that particular seed solution to this coupled system of equations, and that has a solution of this type, which is a kind of one soliton solution. But as you notice, this has parameterizations on the elliptic curve. So the rapidities, or the Backlund parameter here, is a point, namely little p, capital P, on the elliptic curve. Of what form? What do you mean? I don't know the appearance of this curve, but this curve does appear in other. So this is Weierstrass curve actually in disguise. But in a very particular parameterization. And as such, it appears. Sure. But I choose this parameterization because that is the way in which the computation works most conveniently, and in which actually all the quantities are also most conveniently expressed. And as I mentioned in this old work by Datamin, Giamamiwo, and Landau-Lifshitz, they have the same parameterization of the curve actually that appears. Yeah. I can show you the parameterization later on how you parameterize.
No, I just meant that if, for example, you also say that there is something like 2 form, T small, T big, then it just corresponds to this. Right, yeah. But of course you can change it to like.
Yeah, I use this curve because that is the way it most naturally kind of appears in the formulas, basically. Okay, so that is the addressing thing. So what about the integrability aspects? Well, as I mentioned, well, the way we constructed this system, and I go into that a little bit later, is using a technique, a kind of very formal technique. So it has no mathematical rigor, but it works actually, and that's what I call elliptic matrices. And another thing is that this equation can be, by this introducing this quantity, this combination, can be written in a as a coupled system of quad equations, but in multiquartic form, so they are of high degree. And furthermore, well, I mentioned already multidimensional consistency, and it also possesses multi-soliton type solutions, which I will show how they look like. Now, the Lux pair takes this particular form. So this is a zero curvature Lux pair on the lattice. So the zero curvature comes from equating the moves around an elementary quadrilateral of these two matrix equations. And compared to the original H1 equation, if you think away all the terms with G, so this term here, this term here, here and there, then you get the old Lux matrices for the H1 equation, the potential KdV equation, and that has a nice factorization problem. But in this elliptic case, this factorization problem is lost. It no longer factorizes in a natural way. Nonetheless, of course, this Lux pair works and produces the system. If you compute the determinant of this Lux matrix, you get an expression of this form. And there is this, so this is essentially p squared minus k squared. But on solutions of the system, this extra term disappears. And this extra term contains these extra equations in the system, these horizontal and vertical equations. So apart from multidimensional consistency, there's also the question of internal consistency of the system. Are these equations all compatible in each other? And this is something that you can explicitly check. So this was referring to the numbering of the equations in the system. So when you look at initial value problems, for instance, on a configuration in the lattice which is like this staircase, then you can explicitly check that all these equations are compatible with each other. If you impose initial conditions, then the initial conditions with periodic, for instance, boundary conditions, where you repeat after a number of steps, you repeat the values, the initial values, then the W quantities cannot be imposed, but they are self-consistency from the periodicity condition. So if you write down the equations for the W's along, for instance, a number of steps along the staircase, and then you equate this again to W, you get a self-consistent algebraic equation for the W's, and that feeds into the system. So actually writing this as a dynamical map that appears as the reduction or under periodic conditions gives you a dynamical system that is integrable, for which you can compute the invariance, but it's a very complicated system, so I don't write it down. There is also a dual system to this. So we know that, of course, many, like in continuous integrable systems, these discrete systems also come with all kinds of Miura-related integrable situations, so KdV and modified KdV. So the dual system looks essentially is it equivalent to the original system, but now I've introduced some quantities H instead of U and V instead of W, and they are different quantities. In fact, when you go to the G is 0 limit, then the quantity V will obey the modified KdV equation, and H will behave basically as the U quantity. But it disappears from the system because it's always coupled to this modulus G. Now, so this indicates that actually in the elliptic case, all these Miura-related quantities that you know for the KdV system, like modified KdV, Schwarzschild KdV, and so on, they are sitting inside that same system. Okay, so this is about the reduction to, or not a reduction, but actually rewriting the system in quad form in two components. So from the horizontal and vertical relations, which are the last equations, you can actually you can rewrite them in terms of this quantity u minus w over s, which I mentioned before, and then you have you get a quadratic in terms of this combination p plus u minus u tilde and q plus u minus u hat, and from this quadratic you can then solve them in terms of these expressions, where the dp and dq are the discriminants of that quadratic form. So they take this particular shape, and here is where this curve quantity appears. And from these relations, you can then derive also that this combination holds. So this relation between these discriminants. And then from the quad equations in this system, you can derive a number of three equations written in terms of capital U and S. And this is the first equation in the system, this is the second, and this is the third one. And you see that we get here a linear system actually in these combinations of discriminants. So this appears here and there, and here you have the same two combinations of discriminants. You can solve that linear system and then use the last equations to actually find explicit expressions for these discriminants. And what you get then is these expressions here, where the gamma is the determinant of that linear system. So when you equate these expressions with the definitions of the discriminants, which were given, here, these discriminants, you get this coupled multiquartic system that is another alternative way of rewriting this whole system of quad equations. Now, this of course brings in a number of problems, because you then get an issue of branching, and because not all the solutions of the quartics will be valid solution, but that's an issue that I want to avoid at the moment. Another aspect of the integrability is the existence of multi-soliton solutions, and this can be expressed in terms of a kind of Cauchy matrix representation. So the Cauchy matrix actually is a kind of elliptic Cauchy matrix, which has this particular form. This Cauchy matrix also can be written in terms of uniformizing variables, and then it can be expressed in terms of this. Yesterday it was called the Kronecker function in a talk yesterday. I call it sometimes the Baker function, and then you can express in terms of uniformizing variables this Cauchy matrix, which can also, by using the curve relation, also will be related in this way. So the rapidities here, the soliton rapidities, are again points on this elliptic curve, Ki and capital Ki, which are again related through that curve relation. The dynamics is sitting in the variables R, which are like a discrete plane wave vector, so they appear here. And then writing this all in matrix form, you can then find expressions. These are the multi-soliton solutions for these quantities that appear in the system. So little u, little s, little h, w, and v. So as well for the dual system. And the notation here is that the capital K is a diagonal matrix of the capital K rapidities, and the capital little k is the boldface little k is the diagonal matrix of the little k rapidities, all related through this curve relation. The tau function, the relevant tau function, is just in this particular soliton case, is the determinant of one identity matrix plus M, the Cauchy matrix, and that can be expressed in terms of the uniformizing variables of these parameters. So here I've given this parameterization. So the little k variables are given by this combination in terms of Weierstrass P function, and the capital K are Weierstrass P function minus branch point. So E is a particular branch point with kind of half period omega, and that allows you to write the soliton solution in a kind of Hirota form, which is this particular expression. So that is in terms of the Weierstrass sigma function. And the corresponding dynamical variables, the plane wave factors, can be also expressed here in terms of these uniformizing variables, and also with uniformizing variables alpha and beta, which are the ones associated with the lattice parameters. So alpha is related to P and beta is related to Q through these formulas. So zeta here is the Weierstrass zeta function. So this is all pretty straightforward. The expressions for the, and in this respect, actually, it is quite different from the Q4 equations. So if I have time at the end, then I can show you what the soliton solutions for Q4 look like, together with the equation in question, and then can see the differences. So actually, in this elliptic KdV case, the soliton solutions are much more standard and much more straightforward than in the case of the ABS Q4 equation. Okay, and then you can also construct what you can call an elliptic Yang-Baxter map, and that is again using the system. So in the curve relation, you have these combinations of 1 over SS tilde, 1 over SS hat that appear, and that invites you to parameterize this curve relation that appears in the system in this particular way, where you again introduce some uniformizing variables associated with these coordinates x, capital X and little x, which are on once again the same elliptic curve. So little x can be parameterized in this way with a uniformizing variable psi. Eta can be parameterized with uniformizing variable eta, and then the capital X and capital Y that are associated with it take this particular form. And then we can introduce these combinations. So this is just new shorthands for these combinations that appear in the system, P plus U minus W over S, and so on. And the two extra relations horizontally and vertically, they give you just simply these identities. A times capital A is P squared minus X squared, B times little b, capital B is Q squared minus Y squared. So we can, every time when we see a capital A or capital B, we can invert that and write it in terms of little a. And then we have some relations that follow from these definitions, which are these two relations here. And we have the relations that follow from the quad equations in the system, which are these equations here. And this is the first equation, actually, of the system rewritten in these new variables. So the whole system of quad equations reduces to this set of relations, but now essentially in variables that are living on the links of the lattice. And that allows you to follow a construction which is actually due to Papageorgiou, Tongos, and Veselov, which related quad equations to Yang-Baxter maps. So you can follow the same procedure and then create an elliptic Yang-Baxter map that is a map between these pieces of data, namely a combination of little a and the point on the curve, and then a shifted b and the point on the curve. So they live along the horizontal and these horizontal and vertical axis, and that by the Yang-Baxter map gets transformed in this combination of variables, namely a hat and the point on the curve x and x hat, and b and y hat. So this is the Yang-Baxter move, and that Yang-Baxter move by construction follows the Yang-Baxter map relation. So there is a Yang-Baxter quantum Yang-Baxter relations in the sense of maps, of composition of maps. Now, a direct proof, so I still would formulate this as a conjecture, is that it's very difficult to give a direct proof that this obeys the Yang-Baxter relation, because then you have to solve all these implicit equations, and that is a complicated thing to do, which we haven't managed to do yet, but by construction this should work. There's also a kind of unitarity condition of this type, where the R star is associated with the kind of reverse map that comes by reverting the lattice parameters in the system. Okay, so those are a number of results that follow from this elliptic KdV system. Then I want to say something about construction. And the construction follows a rather formal scheme, actually, which I would call elliptic matrices. So what do I mean by elliptic matrices? So elliptic matrices, we know that, for instance, every finite or infinite matrices of standard form can be written in a way where you have a central element. So let me just write it maybe on the board. I can find a chalk. Well, sorry, yeah. Yeah, that's anything new. So you can write any finite dimensional matrix, say A, as a sum of some coefficients, say Aij, with a matrix which is a shift matrix, maybe a shift matrix in this direction, along an infinite shift matrix. Then a matrix which has only one central element on a designated place, and then the shift matrix in the other direction, and that to any power, so I power j. And that produces, and that's basically any finite matrix, depending on whether you choose the sum over A and J as to finite set, in a usual matrix way. And you can think of this suggesting a way to introduce something that you can call an elliptic matrix, namely by, instead of having two shift, just these ordinary shift matrices and its transpose, you have two shift matrices, which I indicate by lambda and L. And these shift matrices are associated with this elliptic curve relation, which once again is the elliptic curve relation that we use all the time. And so this is assumed that these lambda and L, they commute amongst each other, and they have this curve relations. So this is a bit difficult to visualize in terms of conventional matrices, because you can think of basically having two layers of rows and columns, which actually interchange each other according to this curve relation. Nonetheless, this makes perfect sense in the context, so you can define then an elliptic matrix by this type of combination, where O is a rank 1 projector, and obeying this kind of normalization condition. And then we have a particular gradation involved here, which gives a kind of gradation to these matrices with even and odd indices, depending on whether you have a lambda or you don't have a lambda involved. So you can have any power of L, positive or negative, and just first order up to, well, 0 first order in lambda and T lambda. We will also use this kind of expressions, but they can be expressed in terms of those conditions in this particular way. So if you have any arbitrary parameter A here and you want to write down a combination of this form, then you can rewrite it in this way so that you only have first order power in lambda. And then the capital A and little a must again be related through this curve relation. So this can be used as a scheme. It actually has its origin in some kind of Fourier representation of this system, so kind of inverse scattering type scheme. But this formal scheme works very nicely in order to derive the equations. So I don't have a very rigorous approach to the definitions of all these quantities, but it works fine in order to do computations. So then we have to introduce some dynamical variables. So in particular, you can have dynamical variables like little n and capital N. So little n are like the n and m variables that we have in our system. Capital N are not very relevant for our KdV case, but they play a role when you look at the KP generalization, so the multidimensional generalization of the system. And then you have these lattice parameters little p and capital P, which are associated to each other on the curve. And then you can have shift operators. So T here indicates a shift. So I have T and fancy T here. One is a shift in the little n parameters and the fancy shift in the capital N parameters, but we are not going to use it in the KdV system because they basically drop out. But in addition to this, you can also look at a kind of role reversal where the discrete variables and the lattice parameters, they interchange their roles. And now the lattice parameters, they become the variables, and the lattice variables, the discrete variables, they become parameters. And then you can write continuous, differential relations of this type, and they are compatible with these discrete shift variables. So this you can impose simultaneously on such a quantity C, which has a certain representation, but I don't want to go into what it is in terms of this Fourier language. In the KdV case, we impose an addition that you have a symmetry with respect to transposition, and that gives you some extra conditions. So that is actually the condition that is responsible for the fact that these capital P shifts do not appear really in the system for the KdV case, but they do appear in the corresponding KP generalization. Okay, so this is the machinery actually that you can use, and then you have to introduce some kind of formal elliptic Cauchy kernel actually that is written in this structure, and that obeys these two relations. So this in terms of the symbols, this Cauchy kernel takes particularly this form, as we have seen in the soliton solutions, and the corresponding parameterizations of the corresponding variables. They motivate also the corresponding relations for these shift matrices, so lambda and capital L. Once you have all of this, then you can introduce the variables that obey the nonlinear dynamics, and they are introduced through this formula. So the capital U is again an infinite matrix that is constructed out of these linear quantities in this way, or in other words, in terms of this relation. And then you can, from these relations, you can derive that any differential relation that doesn't act on the Cauchy kernel will obey this type of relation, where the differential only acts on the linear quantity C. And the same for the shift variable. Any shift in whatever variable of this quantity U that is defined in this way will obey this relation. So this is a very general structure, which makes it very easy to compute the system and then derive the relations. So in terms of this quantity U, the equations all become nonlinear, or actually kind of Riccati type, and they get this particular structure. So kind of discrete infinite matrix Riccati, and so on and so forth. So we will use these later, but now the game is to get rid of this elliptic matrix structure and actually extract particular scalar quantities that are associated in this way and that obey the relevant equations. And in the KdV case, we have also this extra set of algebraic equations which do not contain any shifts or derivatives, and that allow you to also reduce the system and get the relevant equations. So the quantities that we have seen before in terms of these elliptic matrices, they take this particular expressions. So little u, little s, h, and little v and w, they can be written in this particular way. They are chosen in this way, and then from that system of equations that I showed you, this whole system, you can derive then a number of shift relations. So here the T1 is, for instance, the tilde shift, the T2 is the head shift, and the corresponding parameters P1 and P2 are called P and Q. And then we get this set of relations. And from that set of relations and their corresponding counterparts in the other direction, namely P replaced by Q and tilde replaced by head, you can then derive this KdV, this elliptic KdV system. And actually also the dual system follows in this way. Not only that, but you can also derive the Lux pairs. I don't want to go too much into this, but the Lux pairs actually follow from a similar construction. So let's glance over that. And then the tau function also has play a role. Now, of course, this is a kind of ill-defined quantity. This is a kind of infinite determinant, but we don't need to be afraid of that, because actually by an expansion in terms of matrix invariance, you get a power series in omega, and this contains this projector. So all the quantities by expansion are in principle well defined. And the important thing is that you can derive then some relation for the shifted tau function over tau, which then takes the form of this 2x2 determinant, which involves actually some new quantities that we haven't seen before. So these quantities differ from the ones that I've indicated here. So these are the main quantities of this elliptic KdV system, but there are some new quantities that appear by looking at this tau function, and they essentially take this form. So here's where this inverse of A plus lambda to the inverse comes into play for any parameter A. In particular here for the lattice parameters. So we have quantities like this with a single label. So the parameter, I label these quantities by the parameter. And then we have double labeled quantities as well. So there's a whole structure here that can be set up and which is rather complicated. But it actually gives rise to a 2x2 structure when we somehow collect these quantities in 2x2 matrices in a very particular way, and then the whole structure is starting to make sense. So we can have these single label variables entered in this 2x2 matrix, then the double labeled quantities in this 2x2 matrix, and then it turns out that there's a condition between, or a relation between these quantities, which is of this form. Now, I used here sneakily some kind of capital R and capital S. I'm not suggesting that this is actually an R matrix, but who knows? So here the notation is that E and F and S, they are basically the generators of SL2 algebra. And then we have, of course, the quantity G that appears in the system, and the matrix little g, which is a diagonal matrix with this modulus G involved. So in terms of matrices, actually, we get now a kind of matrix system. And we have, for instance, that the determinants of this matrix V are given by the tau function relations, tau tilde over tau. And then we have this combination of double index matrices shifted, which can be expressed in terms of this matrix V. And this factorizes here on the right-hand side. And then we can combine that with shifted versions and derive this matrix partial difference equations. So this is a 2x2 matrix partial difference equations, which is actually the Schwarzian matrix Schwarzian KdV equation. In some sense, yeah. And this equation in the scalar case was referred to as NQC equation and plays also a role in the ABS list, namely as the Q30 equation in the ABS list. If we take the curve to degenerate, so when we take G is 0, then the Z matrix just has entries on the first row, and then this system becomes just this system of equation, which is actually this Q30 equation. And there's another equation that links the T variable here to this combination there. So this elliptic KdV system is in some sense a reduction of the matrix 2x2 matrix systems, but it's not a simple reduction because there is this condition on the relation between these Z quantities and these V quantities where the curve appears. So it is a very particular type of reduction, which is very well. We don't know yet how to characterize that reduction. Okay, so that's. So there are further combinations that can be considered, namely we can introduce this matrix R. This is motivated by, again, by this elliptic matrix structure where these entries appear in a particular form, but they can be expressed in the known quantities that we have encountered already in this way. And then there is this capital S matrix, which only contains U, little s, and H. And then it turns out that there are these shift relations, and these, what are essentially discrete Miura relations at the 2x2 matrix level. So when we have these equalities here, this is actually a matrix modified KdV. And when we multiply out these two combinations with here minus P minus Q and P plus Q, then we get an equation of this type, which is actually the matrix Schwarzian, the matrix potential KdV equation. But again, it is subject to relations that restrain these variables. Okay, at this point, one could consider also the Lagrange structure. That is a story in its own right, which is this development that we call Lagrangian multiform theory, which is a variational theory for integrable systems, basically, which actually endeavors to build in the multidimensional consistency into the variational formalism. So it would be leading too far to explain that in detail, but the essence is that in this Lagrangian multiforms, the Lagrangian becomes forms, here in this particular case, two forms, and actually a discrete two form, and then the action, the corresponding action, is a sum over any arbitrary surface that you choose. So this is a quadrilateral discrete surface over which you integrate this discrete form. And this becomes then a functional with respect to not only the field variables, but also to the surface. And then the criticality is a criticality condition not only on the variations of the field variables, but also with what you could call discrete infinitesimal deformations of the surface. And that gives you the integrable structure. Okay, so that's all I want to say about this. So this can, in principle, also be developed for this elliptic KdV system, but this is not enough, actually, because this Lagrangian is constrained by some additional relations that are not yet built into the system. So this is not yet the final answer to this story. Okay, and then there is another direction, and that is when you interchange the roles of parameters and discrete variables. So I mentioned already earlier that you can look at differential relations with respect to the lattice parameters. And if you do that, then you can derive this non-isospectral Lux pair or non-isospectral differential problem, which contains some matrices that are constructed from this elliptic matrix system, and which has movable poles. So that's why it's non-isospectral. So this has a pole p squared, which is basically the variable, and here q squared. And that gives rise to non-autonomous, actually, system. So by zero curvature condition, so the matrix coefficients here are given in explicit form here. And again, that is follows from the elliptic matrix system, what these entries are. And when you kind of write out or you compute the zero curvature conditions, you get an extremely complicated system of equations, actually in 6 variables. And these 6 variables are u, s, v, and w. And then some additional variables that are sitting in this elliptic matrix system, u10 and u11. And they look like this. So let me flesh it out. So we have 6 equations, all of second order. And so all going with p squared minus q squared dp dq. And so there are these 2. Then there are these again are 2, one here and one here. And then finally we have more complicated one here and here. Now this looks terrible, but let me just say a few words about this. If we take the curve degenerate, so if you take g equals 0, then actually only 3 of these equations couple together, namely the first three. So these terms disappear, these terms will disappear, and then in the next one, these terms will disappear. And so you get a closed form system only in terms of u, little u, u10, and u11. And that system is actually what we call the generating PDE for the KdV hierarchy. So this is like having the entire KdV hierarchy written in terms of one PDE system, and that appeared in this paper with Andy Hohn and Nalini Joshi. And this has a number of very important properties, one of which is actually that when you look at, so this is a non-autonomous system, and if you do a similarity reduction, a straight similarity reduction on that system, you get the full Penderway-6 equation with all three parameters. And that's the only kind of scalar type system that has three, that gives you full Penderway-6 that I'm aware of. Furthermore, as is shown in some subsequent papers by Tongas, Tsoubalis, and Xenitidis, that system actually is a generalization of the Ernst equations of general relativity, which is itself a kind of curious thing because this is KdV theory. So what has KdV theory to do with general relativity? That is a very strange observation. Okay, so in the final, I've still maybe about 5-10 minutes or so. Let me make a comparison with between this elliptic KdV system and the so-called Q4 equation of the famous ABS list, which is this equation here. So this is a scalar quad equation. Again, it has variables shifted along an elementary quad, and it has now lattice parameters on, again on an elliptic curve, but this is a Jacobi curve in this case. And I'll give you a little more detail in the next slides. Well, that was too early. And it has this particular form. So this combination here, this combination of the four variables along multiplied along the quad, that is a bit reminiscent of what we have seen in this multiquartic form of the elliptic KdV. But so far, we don't know really what the connection is between these two systems. Now, this Q4 equation arose first, or it was first discovered by Seva Adler in 1997, I think, as the permutability condition for the Backlund transforms of the Khrushchev-Novikov equation. The Khrushchev-Novikov equation is a continuous analog of KdV, which also has an elliptic curve in it. And when Adler looked at the Backlund transform, he derived the permutability condition, and that gives rise to this lattice equation. And then it appeared again 2 or 3 years later in the ABS list in the classification as the top equation of the ABS list of scalar quad equations that are multi-affine, have multi-affine form and are multidimensionally consistent. Now, so far we don't really know what the underlying inverse structure is of this Q4. There's very little results known about Q4 so far. The suspicion is that Q4 is actually akin to Landau-Lifshitz in some sense, and as a kind of zero spin limit of Landau-Lifshitz. But Landau-Lifshitz would have a different Cauchy kernel. It would have this kind of upside down kernel compared to the kernel that appears in the elliptic KdV. So this is the kernel essentially that is in the elliptic KdV system, and this is the kind of kernel that you can find in Landau-Lifshitz treatment of Landau-Lifshitz Soliton solution. So what do we know about Q4 solutions? Well, not much, as I said, but we did construct in a paper with James Atkinson, we construct the n-soliton solutions, which actually are solutions of bielliptic type. So what does it mean by elliptic type? It means that there are actually two elliptic curves with different moduli that appear in those solutions. And here are the solutions. So here's the Q4 equation. Actually, this particular form of the Q4 equation was due to Jarmo Itarinta, who kind of rewrote the Q4 of Adler. Adler's form is like Weierstrass form, and this is like the Jacobi form of the Q4 equation. They are kind of equivalent, but this is in some sense kind of easier to actually to write down and also to study. Now, what do the soliton solutions look like as we constructed in our paper? So they look in the following way. They are like a seed solution U0 multiplied by a ratio of tau functions. And these tau functions take this particular form, so they are called FNG. And they are here written in terms of Jacobi theta functions, but with parameters that are deformed parameters. So we have parameters of the curve as they appear in the equation, and this is the curve as it appears in the equation with parameterization with little p, little q, capital Q. But then it turns out that in order to find the soliton solutions, you have to deform the curve with a parameter, actually, and that changes the modulus of the curve. So we have parameters, so there are parameters with star here, which are related to a deformed curve. And here are these kind of combinations that, again, in terms of Jacobi theta functions, which contain actually both the deformed and undeformed rapidities. So these little l's and little li and little star li's, they are the rapidities of the soliton solutions, but they live on two different curves. The curve, we have the curve that of the original curve of the equation, which is this one, with a modulus k, and then we have the curve of the seed solution, which is this solution here, with modulus k star. And this k and k star, these two curves are related in a very implicit way, namely through this relation. So k star plus 1 over k star, this is the modulus of the deformed curve, is related to a Backlund parameter, but this Backlund parameter, which is also a point, but now a point on the original curve. So this contains the original correspondence between these different parameters, the undeformed and the deformed parameters. So this is a really very interesting bi-elliptic structure that appears in the soliton solutions of these Q4 equations. And as an upshot, and this is my last transparency, you can actually, what makes these soliton solutions work are some new type of addition formulas, which are not like any of the usual addition formulas that we know and find in the textbooks on elliptic functions, but they are elliptic addition formulas involving two elliptic curves, one with modulus k star and another with modulus k. So this is a particular example of such an addition formula, and where the different parameters, the alpha stars and the alphas and betas, are related through these relations involving also elliptic curves with a deformation parameter theta. So this opens up, I think, an interesting new kind of, maybe even a new kind of aspects of elliptic functions that maybe were not known before. Well, if anybody knows and has seen this kind of thing before in other contexts, then I would be happy to learn about it. But maybe this also perhaps makes a connection with modular forms. So this is basically where I wanted to stop. Thank you for your attention.
Thank you very much. Let me see if there are any questions. Online? Zoom? No questions on Zoom? Questions from the audience?
Hmm?
Can you make exactly the discrete and continuous parts of it on the multiple parameters?
Well, out to the you mean this page?
So do you have? Can you elaborate again on the interpretation of this discrete and the continuous part?
Say that again.
So this multiform contains both discrete and continuous parts.
No, not this one though. So if you want, so we have a continuous system as well. This this equation for S also, there are also continuous equations. And that would mean that when you write down this multiform, well, first of all, if you have more variables from your system, you get more contributions to this multiform. So you get extra wedge factors here. But these wedge factors can also contain continuous, so usual differentials. Yeah.
You can extend this discrete multiform Lagrangian with the continuous.
You can do that, yeah. And we have worked out examples, not in this particular case of this elliptic KdV, but for other cases you can do that.
So my second point: what is the interpretation of these two, and what are the examples? Is that what this?
One example actually was, for instance, in a paper that 1 or 2 years ago about semi-discrete and discrete KP forms. So you have lattice KP, which has a multiform structure with discrete form structure. Then you have a semi-discrete version, which is compatible with the fully discrete version. And then you can write a multiform which contains a fully discrete free form in that case, with a semi-discrete free form where you have wedge factors between discrete parts and also fully continuous. So that's
a canonical KP example you're saying.
Yeah, KP, but it's also the discrete KP equation. It contains that in one system, basically. Yeah.
Okay, I can ask you more maybe in private, but for the Cheng Simons. So.
Cheng Simons. Okay.
Okay. Other questions? All right. Well, let's thank Frank again.
Okay, thank you.